Welcome to Quietly Made. I am so glad you have found your way here tonight. This is a space for the curious and the weary, a place where we explore the vast, invisible infrastructures of our world, while giving your mind the permission it needs to simply rest. Before we begin, I invite you to join our community by subscribing and leaving a comment. I often wonder where these stories find you tonight. If you feel inclined, please leave a comment sharing what part of the world you are in and the hour you are settling into sleep. It is a small way for us to feel the quiet connection of this community, scattered across different time zones, but sharing this same moment of rest. If you fall asleep, that is exactly what should happen. You are safe here. You can always come back tomorrow and pick up exactly where you left off. Adjust your pillow. Take a deep, slow breath in and let it out. Let your mind drift as we begin. Tonight, we turn our attention to the quiet assembly of the steam engine, to the hiss of vapor escaping through valves, to the rhythmic stroke of pistons moving in brass cylinders, to the engineers who understood that water, when boiled, possessed a force that could move mountains, to the metal workers who learned that cast iron could contain pressures that would burst wood, that copper tubes could channel steam without corroding, that the simple act of condensing vapor could create a vacuum powerful enough to pull. This is not a story of sudden invention. It is a story of gradual refinement, of boilers that ruptured and killed their operators, of pistons that seized from inadequate lubrication, of governors that failed to prevent engines from destroying themselves. It is a story written in the language of thermodynamics and metallurgy, in the clang of hammers shaping cylinder walls and the patient boring of holes that had to be true within thousandths of an inch. We begin not with an engine, but with a question that occupied minds for centuries. How do you capture the power of heat and transform it into motion? Fire had served humanity since before history began. It cooked food, warmed shelter, hardened clay, softened metal. But fire itself could not move things. It could heat air, making it rise. But this rising could not be harnessed for useful work. It could boil water, creating steam that escaped into the air, its energy dissipating uselessly. The insight that changed everything was recognizing that steam occupies more space than the water it came from. Much more. Water, when converted to steam at atmospheric pressure, expands roughly 1,600 times. This expansion represents force. If contained, if directed, this force could push against something, could move it, could do work. The earliest attempts to use steam were crude. Pistons in cylinders, steam admitted beneath them, lifting them. The problem was returning the piston to its starting position. Gravity could pull it down if the piston was heavy, if it was oriented vertically, but this wasted half the cycle. What was needed was a way to pull the piston down as forcefully as steam pushed it up. The solution was vacuum. Not a perfect vacuum, that was impossible to achieve, but a partial vacuum, a space where air pressure was reduced. Atmospheric pressure, the weight of air pressing down on everything at sea level, amounts to nearly 15 pounds per square inch. This seems modest until you calculate the total force on a large surface. A piston a foot in diameter has an area of over 100 square inches. Atmospheric pressure on such a piston exerts more than a ton of force. Creating a vacuum required removing air from a space. Simply sealing a container does not create vacuum. Something must displace the air. Steam could do this. Admitted to a cylinder, it filled the space, pushing air out through a valve. Once the cylinder was full of steam, the valve was closed. Then the steam was condensed, turning back to water, which occupied far less space. The remaining air was insufficient to fill the cylinder. An atmospheric pressure pushed the piston inward. This was the atmospheric engine. Steam did not push the piston directly. Rather, steam filled the cylinder, was condensed, and atmospheric pressure did the pushing. The stroke was powerful, thousands of pounds of force, but the cycle was slow. Time was needed for steam generation, for condensation, for the piston to complete its motion. The boiler that generated steam was initially nothing more than a large kettle over a fire. Water filled the kettle. Flames heated it. Steam rose from the surface. Simple. But as engines grew larger, requiring more steam, the simple kettle proved inadequate. The problem was heat transfer. The fire touched only the bottom of the kettle. Heat had to conduct through metal, then into water. Metal is a good conductor, but the process still takes time. To boil water faster, you need more surface area in contact with flame, or hotter flame, or both. Boiler design evolved toward maximizing this contact. Flues, tubes carrying hot gases from the fire, passed through the water, heating it from within. The gases traveled through multiple passes, extracting as much heat as possible before exhausting to the chimney. The water surrounded these hot tubes, absorbing heat from all sides. But this created new dangers. The pressure inside the boiler increased with temperature. Water at atmospheric pressure boils at 212 degrees. Under pressure, the boiling point rises. At 15 pounds per square inch above atmospheric pressure, water boils at 250 degrees. At higher pressures, higher still. The metal of the boiler had to contain this pressure. Cast iron was strong in compression, but brittle. A crack could propagate suddenly, catastrophically. Wrought iron was tougher, more resistant to sudden failure, but harder to cast into the shapes needed for boilers. The joints where sections of the boiler met were particular points of weakness. Rivets held plates together, each rivet a potential leak path. The rivets had to be perfectly formed, the holes perfectly aligned, the plates perfectly flat. Imperfections meant leaks, and leaks under pressure could erode metal, widen gaps, lead to failure. Testing boilers was dangerous work. A boiler was filled with water, heat applied, pressure allowed to build. Inspectors watched for leaks, for bulging plates, for any sign of weakness. Sometimes the signs were subtle. Other times, the boiler simply exploded. The stored energy of pressurized steam released in an instant, tearing metal apart, hurling fragments, scalding anyone nearby with superheated water flashing to steam. These disasters led to standards, to regulations, to required safety valves that would open if pressure exceeded design limits. The safety valve was a simple device, a valve held closed by a weight or a spring. If pressure rose too high, it overcame the restraining force. The valve opened, steam escaped, pressure dropped. But the valve had to be reliable. It could not stick closed. It could not be tampered with by operators seeking more power from their engines. Boiler insurance emerged. Companies that inspected boilers, certified them safe, insured against explosions. The inspectors became experts in metallurgy, in stress analysis, in the subtle signs of fatigue and corrosion. They rejected boilers that operators insisted were fine. They mandated repairs that seemed unnecessary, and they saved lives. Though the lives saved were uncounted, the disasters that never happened invisible. The cylinder, where steam did its work, had to be machined with precision that pushed the limits of available tools. The piston fit inside the cylinder with only a small gap, ideally a few thousandths of an inch. Too large a gap, and steam leaked past the piston, reducing power. Too small, and friction between piston and cylinder wall consumed the power the steam provided. Achieving this precision required boring the cylinder, rotating a cutting tool inside it, gradually enlarging the hole, cutting away metal until the diameter was correct and the surface was smooth. The boring bar had to be rigid, the cutting tool sharp, the rotation steady. Any wobble, any deflection, and the cylinder would not be truly round. Early cylinder boring was done by hand, with tools that could not maintain precision over the length of large cylinders. The result was cylinders that were wider at one end than the other, or that bulged in the middle, or that had surfaces rough enough to score the piston. Improvements in boring techniques, in the rigidity of machines, in the quality of cutting tools, allowed cylinders to be made that were round and smooth and parallel. This improvement in precision directly translated to improvement in engine performance. Less steam leaked past the piston. Less power was lost to friction. The same boiler could power a larger load. The piston itself was a metal disc fitted with packing, rings of rope or leather or metal that sealed against the cylinder wall. The packing had to be soft enough to conform to irregularities in the cylinder, tough enough to withstand the heat and pressure of steam, and lubricated enough to slide without excessive friction. Piston rings, when they evolved, were split rings of metal that pressed outward against the cylinder wall. The ring's own elasticity created the sealing force. Wear gradually reduced the ring's effectiveness, but they could be replaced without replacing the entire piston, a significant economic advantage. The piston connected to a piston rod, a long shaft extending out of the cylinder. The rod had to be strong. It transmitted thousands of pounds of force. It had to be smooth. It slid through a gland in the cylinder head, and roughness would damage the packing that sealed around it. It had to be straight. Any bend would cause it to rub against the gland, creating friction, wearing both rod and packing. Motion from the piston, reciprocating back and forth, had to be converted to rotary motion, to be useful for most applications. A wheel or a shaft needed to spin continuously, not jerk back and forth. The mechanism that achieved this conversion was the crankshaft, borrowed from earlier technologies like the potter's wheel and the treadle lathe. The piston rod connected to one end of a beam, a large lever pivoting at its center. The other end of the beam connected to the crankshaft through a connecting rod. As the piston moved, the beam rocked, and the connecting rod pushed and pulled on the crankpin, causing the crankshaft to rotate. This seems simple in principle, but the geometry created challenges. The connecting rod changed angle throughout the rotation, causing the force on the crankpin to vary. At some positions, the mechanical advantage was high, at others, low. The motion was smooth only if the crankshaft had momentum, a heavy flywheel attached to it that stored energy during the power stroke and released it during the return stroke. The flywheel was a massive wheel, sometimes weighing tons, its rim heavy, its spokes strong enough to withstand the centrifugal force of rotation. The flywheel's inertia smoothed the engine's operation, preventing it from stalling when resistance increased, preventing it from racing when resistance decreased. Balancing the flywheel was critical. Any asymmetry, any heavy spot would create vibration as the wheel rotated. The vibration would stress bearings, loosen bolts, eventually cause failure. Foundries cast flywheels, then machined them on lathes, turning the rim true, drilling holes to remove weight from heavy sections, achieving balance that allowed the wheel to spin smoothly at speeds where imbalance would be destructive. Lubrication was essential everywhere. Metal moved against metal. The bearings where the crankshaft rotated, the gland where the piston rod slid, the pins connecting the various linkages, all required lubrication to prevent destructive wear. Early engines used animal fats, tallow, lard, as lubricants. These were cheap, available, reasonably effective at the low speeds and moderate temperatures of early engines. But as engines grew more powerful, as speeds increased, as steam temperatures rose, animal fats proved inadequate. They broke down in heat, becoming thin and useless, or they oxidized, becoming thick and sticky. Mineral oils, derived from petroleum, offered superior properties. They remained stable at higher temperatures, did not oxidize as readily, could be refined to specific viscosities. But mineral oils were initially scarce, expensive, available only from specific geological formations. The quantity of lubricant needed was substantial. A large engine might consume gallons per day, the oil dripping from bearings, carried away by steam, lost to evaporation. Closed lubrication systems that recirculated oil were developed, using pumps to deliver oil to bearings, collecting it in sumps, filtering it, returning it for reuse. This reduced consumption dramatically, but added complexity. The quality of lubrication determined bearing life. A bearing starved of oil would heat from friction. The metal would soften. Seizure would occur. The engine would grind to a halt, the bearing destroyed. Possibly the journal, the shaft surface it rode on, damaged as well. Repair required disassembly, replacement of damaged parts, careful reassembly, a process that could take days. Operators learned to listen to their engines. to hear the subtle changes in sound that indicated developing problems. A squeal suggested inadequate lubrication. A knock suggested wear, play in bearings, looseness in connections. The experienced operator knew their engine's normal sound so well that any deviation was immediately apparent. Governing the engine's speed was necessary for most applications. An engine powering a mill needed to maintain constant speed despite variations in load. More fabric being processed, then less, then more again. Without governing, the engine would slow under heavy load, potentially stalling, or race under light load, potentially destroying itself. The centrifugal governor provided elegant mechanical feedback. Two weighted arms were attached to a vertical shaft driven by the engine. As the shaft spun faster, centrifugal force pushed the weights outward. As it spun slower, they fell inward. The position of the weights controlled a valve that admitted steam to the cylinder. When the engine ran too fast, the weights flew outward. The valve closed partially. Less steam entered. The engine slowed. When it ran too slowly, the weights fell inward. The valve opened wider. More steam entered. The engine accelerated. The system sought equilibrium, a speed where centrifugal force balanced the spring or weight restraining the arms. This negative feedback loop was remarkably effective. The governor responded automatically, continuously, requiring no human intervention. It allowed engines to maintain nearly constant speed across varying loads, a capability that transformed manufacturing, allowing precision processes that required steady, predictable power. But the governor was not perfect. It responded to speed changes after they occurred, introducing a lag. If the governor was too sensitive, it overreacted, causing speed to oscillate. Hunting, this behavior was called. If too insensitive, it allowed excessive speed variation. Tuning the governor, adjusting the weight of the arms, the stiffness of restraining springs, the linkage to the steam valve, required experience and patience. The condenser, in engines that used one, converted steam back to water after it had done its work in the cylinder. This served two purposes. It created the vacuum that allowed atmospheric pressure to push the piston, and it recovered water that could be returned to the boiler, reducing the need for fresh makeup water. The simplest condenser was a tank of cold water. Exhaust steam from the cylinder was directed into this water, where it bubbled through, condensing, its heat warming the water. But warm water is less effective at condensing steam, so the water had to be circulated, cold water added, warm water removed. Surface condensers improved efficiency. These used tubes through which cold water flowed. Steam surrounded the tubes, condensing on their exterior without mixing with the cooling water. This kept the condensate pure, free from impurities in the cooling water, suitable for return to the boiler without treatment. The condenser operated under vacuum, below atmospheric pressure. This required all connections to be tight. Any leak allowed air to enter, degrading the vacuum, reducing efficiency. An air pump was needed to remove non-condensable gases. Air that leaked in, gases dissolved in water, maintaining the vacuum despite these intrusions. The air pump was a small, reciprocating pump, often driven by the same engine it served, operating continuously, extracting air and gases from the condenser. The pump's pistons and valves had to seal well, had to tolerate the corrosive environment of steam condensate, had to operate reliably for thousands of hours. Multiple expansion, the use of steam in 2 or more cylinders at successively lower pressures, increased efficiency substantially. Steam from the boiler entered a small, high-pressure cylinder. After pushing the piston in this cylinder, the partially expanded steam, still at considerable pressure, passed to a larger, low-pressure cylinder where it expanded further. By expanding steam in stages, extracting work at each stage, more of the heat energy in the steam was converted to mechanical work. The efficiency gain was significant. Compound engines used perhaps half the fuel of simple engines for the same work output. But compound engines were more complex. They required 2 or more cylinders, precisely timed, coordinated in their action. The valve gear that controlled steam admission and exhaust had to be carefully designed, each cylinder receiving steam at the right moment, exhausting it at the right moment. The cylinders operated at different temperatures. The high-pressure cylinder hot, the low-pressure cylinder cooler. This temperature difference caused differential expansion of the metal, creating alignment challenges. Bearings had to accommodate slight movements, connections had to allow for thermal growth, or stresses would develop that could crack castings. Triple expansion engines carried the concept further, adding a third cylinder at intermediate pressure. These were the pinnacle of reciprocating steam engine development, achieving efficiencies approaching 20%, meaning 1/5 of the heat energy in the fuel was converted to useful work, with the remainder lost to the exhaust, to the condenser cooling water, to radiation from hot surfaces. 20% seems poor by modern standards, where internal combustion engines exceed 30%, where combined cycle power plants approach 60%. But for their time, steam engines represented a vast improvement over earlier power sources, over water wheels dependent on flowing streams, over windmills dependent on fickle breezes, over animal power limited by muscle strength and endurance. The applications of steam power were nearly limitless once reliable engines were developed. Mines used steam engines to pump water, allowing deeper excavation than human or animal-powered pumps could achieve. The engines ran continuously, day and night, moving thousands of gallons per minute, keeping mines dry enough to work. Textile mills installed steam engines to power spinning and weaving machinery. A single engine, through a system of belts and shafts, could drive hundreds of machines. The mill was no longer constrained to locations near flowing water. It could be built anywhere coal could be delivered, which in practice meant anywhere with access to canals or railways. The railways themselves were perhaps steam's most visible application. The locomotive was a mobile steam engine, carrying its boiler, its fuel, its water, traveling on rails, pulling loads that would require dozens of horses. The locomotive's freedom of movement, its ability to go wherever rails were laid, its power vastly exceeding animal sources, reshaped transportation, commerce, the very geography of development. Ship propulsion transitioned from sail to steam, a change that was resisted. Sailors loved their craft, mistrusted machinery, valued the art of working with wind and current. But steam offered independence from weather. A steamship could maintain schedule, could go where wind would not take it, could maneuver in confined waters where sailing ships needed tugs. The marine engine faced unique challenges. It had to tolerate motion, vibration, salt air, limited space, weight constraints. It had to be reliable. Failure at sea could be fatal. It had to be efficient. Fuel was heavy, taking cargo space, limiting range. Marine engines evolved toward compactness, toward robustness, toward designs that prioritized reliability over maximum power. The engine room of a steamship was a hot, noisy, cramped space, smelling of oil and steam, where engineers tended their machinery with skill, born of long experience. The people who operated steam engines developed deep relationships with their machines. An engineer, the title given to those who ran engines, learned every quirk, every tendency of their particular engine. They knew how it sounded when running well, could detect the slightest irregularity. They knew how much load it could carry, how to nurse it through difficult starts on cold mornings, how to shut it down safely after a long day's work. The ritual of starting an engine was elaborate. The boiler had to be warmed slowly. Too rapid heating could crack plates, loosen rivets. Water level had to be checked, fuel loaded. The fire built up gradually. Steam pressure rose over hours, the safety valve occasionally lifting to release excess pressure. The steam gauge watched constantly. Once pressure was sufficient, the engine could be started. Valves were opened, admitting steam to the cylinder. The flywheel might need to be turned by hand, positioning the crank away from dead center, where it could not start on its own. The first few revolutions were hesitant, the engine finding its rhythm. Then it settled into steady operation, the governor taking control, maintaining speed. During operation, the engineer monitored constantly. Water level in the boiler, too low and the metal could overheat, too high and water could be carried into the cylinder, causing hydraulic lock. Steam pressure, too low and power was insufficient, too high and the safety valve would lift, wasting fuel. Bearing temperatures, hot bearings meant inadequate lubrication, impending failure. At day's end, shutting down reversed the starting process. The fire was allowed to die. Steam pressure bled off. The engine coasted to a stop. Everything was secured. Valves closed, drains opened, surfaces cleaned, small maintenance tasks performed. The engine room was left tidy, ready for the next day's start. Maintenance consumed significant time and resources. Boilers required regular inspection, cleaning of scale, mineral deposits from water that accumulated on heating surfaces, reducing heat transfer. The scale had to be chipped away, a tedious process requiring the boiler to be drained, cooled, opened, worked on from inside. Valve gear needed periodic adjustment. Wear in pins and bearings created play, causing timing to drift. The valves might open too early, too late, stay open too long, close too soon. Adjusting the eccentric rods, the valve stems, the linkages, required patience and precision, often involving trial and error, running the engine, observing its behavior, stopping to make adjustments, repeating until performance was optimal. Bearings were inspected, their babbitt, a soft alloy that formed the bearing surface, checked for wear. Worn babbitt was scraped out, new metal poured in, the bearing reassembled. This required the engine to be disassembled to some degree, the shaft removed or at least loosened, the bearing accessible. Piston packing was replaced when it leaked excessively. The piston had to be withdrawn from the cylinder, old packing removed, new installed, everything reassembled with care to ensure alignment. A misaligned piston would score the cylinder, creating damage far worse than worn packing. The parts themselves had to be manufactured or obtained. In early days, engines were largely custom built, each part unique to that engine. If a component failed, a replacement had to be fabricated, often by local foundries and machine shops working from measurements of the broken part. Standardization emerged slowly. Common sizes for cylinders, for shafts, for bearings allowed parts to be manufactured in quantity, held in inventory, available for replacement without custom fabrication. But true interchangeability, where any part from a batch would fit any engine of that model, required precision beyond what most manufacturers achieved until late in the steam era. The fuel that fed steam engines was primarily coal, burned in furnaces beneath the boilers. Coal varied widely in quality, in heat content, in ash content, in how readily it ignited. Anthracite, hard coal, burned hot and clean, but was slow to ignite and expensive. Bituminous coal, softer, ignited more easily, but produced smoke and left more ash. The fireman, the person who fed the fire, developed skill in managing combustion. Coal was not simply shoveled into the furnace indiscriminately. It was spread evenly, thin layers allowing air to reach each piece. The grates beneath the fire allowed air to flow upward through the fuel bed, providing oxygen for combustion. Controlling airflow controlled combustion rate. Dampers in the flue adjusted draft. The flow of air pulled through by the chimney. More draft meant more air, hotter fire, more steam. Less draft reduced combustion, conserving fuel when full power was not needed. The smoke from the chimney indicated combustion quality. White smoke meant too much air, incomplete combustion. Black smoke meant insufficient air, unburned carbon escaping. The ideal was a light grey, nearly invisible, indicating efficient combustion with minimal waste. Ash accumulated in the ash pit beneath the grates, requiring periodic removal. If allowed to build up, it blocked airflow, reduced combustion efficiency. The ash was raked out, often while the fire still burned, a hot, unpleasant task that exposed the fireman to intense heat and choking dust. Water for the boiler had to be relatively pure. Minerals dissolved in water would precipitate when heated, forming scale on boiler surfaces. Scale was an insulator, reducing heat transfer, causing the metal beneath it to overheat. Scale buildup was gradual but relentless, requiring regular cleaning to prevent damage. Water treatment developed to address this. Chemicals added to the boiler water prevented scale formation or made the scale that did form softer, easier to remove. Feed water heaters used exhaust steam to preheat the water before it entered the boiler, improving efficiency and driving off dissolved gases that could cause corrosion. Some installations used distilled water produced by condensing steam, inherently pure. This was ideal but required means of producing it, typically through a dedicated evaporator or by capturing condensate from the engine's exhaust. The feed pump that supplied water to the boiler was critical. If it failed, water level would drop, potentially leading to catastrophic boiler failure. Redundant pumps, backup systems, reliable mechanical designs, all were employed to ensure water feed could not be interrupted. The injector, a device that used steam to force water into the boiler, was a clever alternative to mechanical pumps. Steam from the boiler, moving at high velocity through a nozzle, entrained water, accelerating it to sufficient velocity to overcome boiler pressure and enter despite being at atmospheric pressure initially. The injector had no moving parts, was simple, reliable, though somewhat mysterious in its operation even to those who used it daily. The efficiency of steam engines, the fraction of fuel energy converted to useful work, was limited by fundamental thermodynamic principles. Heat flows from hot to cold. Work can be extracted from this flow, but not all the heat can be converted to work. The theoretical maximum efficiency depends on the temperature difference between the heat source and the heat sink. Steam engines operated between the temperature of steam in the boiler, perhaps 400 degrees for a high-pressure engine, and the temperature of the condenser or exhaust, perhaps 150 degrees for a condensing engine. This temperature range, measured in absolute terms, limited efficiency to roughly 25% under ideal conditions. Real engines fell short of this ideal due to losses, friction, radiation, incomplete expansion, throttling losses in valves, heat lost through cylinder walls during each cycle. Achieving even 15 to 20% efficiency required careful design, good maintenance, skilled operation. Efforts to increase efficiency focused on raising steam temperature and pressure, on improving insulation to reduce heat loss, on expanding steam more fully through multiple cylinders, on reducing friction through better lubrication and precision manufacturing. Some experimental engines operated at extreme conditions, steam temperatures exceeding 700 degrees, pressures exceeding 500 pounds per square inch. These achieved higher efficiencies, but required exotic materials, faced accelerated wear, were complex and expensive. They remained rarities, confined to specialized applications where efficiency justified their cost. The sound of a steam engine in operation was distinctive. The exhaust puffed rhythmically, each stroke releasing a burst of steam that condensed into white clouds in cool air. The beat was steady when running at constant speed under steady load, governed precisely, a mechanical heartbeat. The hiss of steam leaking from packing glands, from valve stems, was continuous, a background accompaniment to the dominant exhaust note. Bearings hummed or rumbled depending on their condition. The belt-driving auxiliary equipment sang, a note that changed pitch slightly with load. The fire in the furnace roared when the fireman opened the door to add coal, visible light and heat emanating. Then the door clanged shut and the roar became muffled, contained within the firebox, expressed only through the chimney's draft. Water in the boiler bubbled and churned, audible when standing close, a reminder of the violent phase change occurring, of the energy being absorbed and stored as latent heat in the steam. These sounds became familiar to those who worked around steam. They indicated normal operation, and any deviation, a change in rhythm, a new noise, silence where sound should be, commanded immediate attention. Accidents, though operators tried to prevent them, occurred with grim regularity in the early decades of steam power. Boiler explosions were the most feared, sudden and devastating. The stored energy in pressurized water was immense. When a boiler failed, that energy was released instantly, tearing the boiler apart, hurling fragments, collapsing buildings, killing anyone nearby. Investigations after explosions usually found causes: low water level exposing plates to direct flame, weakened metal from corrosion or previous damage, safety valves that had been tampered with or failed to operate. The lessons learned led to improved designs, to regulations, to inspector training. But knowledge spread slowly. What was learned in one place might not reach another for years. Operators repeated mistakes others had already made, paying the same price in lives and property. Scalding injuries from leaking steam lines, from bursting hoses, were common. Steam at pressure could cut through clothing, through skin, causing deep burns. Workers learned to respect steam, to approach valves cautiously, to stand aside when opening lines that might be pressurized. Mechanical failures, a connecting rod breaking, a flywheel bursting, a belt snapping, could hurl heavy parts with lethal force. Guarding machinery, keeping bystanders clear, maintaining equipment to prevent failures, all became standard practice, though enforcement was often lax. The human cost of steam power is difficult to quantify. Records are incomplete. Many incidents went unreported. The injured or killed were often not named in accounts. But it was significant, paid in the bodies of workers who operated and maintained the machines. The economic impact of steam power was profound. Manufacturing could locate where markets and labor were, not where water power was. Factories grew larger, producing more goods at lower cost per unit, serving wider markets. Transportation costs fell as steam locomotives and ships moved goods faster, more reliably than animal power or sail. This expanded trade allowed regional specialization, enabled economic integration across vast distances. Urbanization accelerated. Workers migrated to factory towns, to cities where steam-powered industry concentrated. Populations grew beyond what local agriculture could support, fed by food shipped from distant farms on steam-powered railways. Capital accumulated to those who owned the engines, The factories, the railways, labor, displaced from traditional crafts by mechanized production, sought employment in factories where wages were paid, where work was steady if not always secure, where conditions were often harsh. The social changes intertwined with steam power are impossible to separate cleanly. Steam did not cause these changes alone, but it enabled them, accelerated them, shaped their character. A world with steam power evolved differently than it would have without. The decline of steam began as alternative power sources emerged. Internal combustion engines offered higher power-to-weight ratios, easier starting, no warm-up period, suitability for vehicles where boiler and fuel supplies were impractical. Electric motors, powered by distant generators, offered clean operation, precise control, no need for on-site fuel handling. Steam persisted longest where its characteristics remained advantageous. In large central power generation, where turbines replaced reciprocating engines, achieving higher efficiencies. In ships where marine turbines could be made very large, very powerful. In industries with waste heat or biomass, fuels suitable for boilers. But reciprocating steam engines, the type that had powered the industrial transformation, gradually disappeared from factories, from locomotives, from all but specialized or heritage applications. The last were retired, scrapped for their metal, or preserved as monuments to a technology that had reshaped civilization. The knowledge of operating and maintaining them faded as the generation that knew these machines aged and passed. Preserved engines often sat silent, their operation too complex, too risky for volunteers without proper training. Some museums and preservation societies maintained operating examples, training new engineers in the old skills, keeping alive traditions of steam operation. What remains of the steam engine's legacy is not the machines themselves, most long gone, but the infrastructure they made possible, the manufacturing techniques they drove, the understanding of thermodynamics and mechanical engineering they demanded. The factories built to house steam engines still stand, converted to other uses. The railways they powered still carry freight and passengers, though now behind diesel or electric locomotives. The cities they helped build continue to grow. The engineering disciplines steam power fostered, thermodynamics, materials science, precision manufacturing, advanced beyond steam, applied to new technologies. The problems steam engineers solved, how to contain high pressures, how to convert heat to work, how to control speed automatically, inform contemporary engineering. The museums that display steam engines present them as curiosities, as artifacts of a vanished era. Visitors marvel at their size, their complexity, their raw mechanical power. They struggle to imagine these machines in daily operation, to hear the sounds, to smell the coal smoke and hot oil, to feel the heat and vibration. Preservationists who maintain operating steam engines speak of their appeal, the directness of cause and effect, the visibility of how they work, the tangible connection between fuel and motion. Unlike modern machines, where processes happen inside sealed units, where electronic controls obscure mechanical reality, steam engines reveal themselves. You can watch the piston move, see the valve gear operate, understand through observation how steam pressure becomes rotary motion. This transparency made steam engines teaching tools. Engineers learned on steam because the principles were visible, the consequences of poor design or operation immediate. Many who never worked with steam professionally retained affection for these machines, appreciation for their engineering, respect for those who built and operated them. The transition away from steam was not mourned universally. Steam engines were dirty, inefficient by modern standards, labor-intensive to operate. They required skill and constant attention. They failed in ways that were dangerous. The alternatives, when they arrived, offered genuine improvements: cleaner operation, higher efficiency, easier control, safer operation. Yet something was lost in the transition. The steam engineer's craft, developed over generations, became obsolete. The intimate knowledge of a particular engine, its quirks and tendencies, became unnecessary when engines were replaced by electric motors, requiring only that someone turn them on. The community of steam operators, the shared knowledge and experience, dissolved as the machines disappeared. The younger generation saw no future in learning skills for obsolete technology. The knowledge holders aged, retired, passed away, taking with them understanding that was not fully documented, that existed in practical experience more than in written form. Some attempted to preserve this knowledge. Manuals were written, photographs taken, oral histories recorded, but words and images could not fully capture what it meant to operate a steam engine, the judgment required, the sensory cues, the physical effort. Steam power plants, using turbines rather than reciprocating engines, continued to generate electricity long after reciprocating engines disappeared from other applications. The turbine, developed later than reciprocating engines, offered advantages for power generation: smooth rotation, high speed, suitable for direct connection to generators, efficient operation at large scales. The steam turbine works on different principles than reciprocating engines. Steam passes through rows of blades, pushing them, spinning a rotor at high speed. The steam expands through multiple stages, each extracting energy until it exhausts at low pressure to a condenser. Turbines could be made enormous, producing hundreds of megawatts from a single unit. They operated efficiently at pressures and temperatures that would destroy reciprocating engines. They had fewer moving parts, required less maintenance, operated more reliably. Power plants burning coal, oil, or natural gas, or using nuclear heat, produced steam that drove turbines coupled to generators. This remained the dominant method of electricity generation well into the current century, gradually supplemented by renewables, by natural gas turbines, but not entirely displaced. These modern steam plants bear little resemblance to early steam engines. The boilers are massive structures, multi-story buildings containing thousands of tubes. The turbines spin at thousands of revolutions per minute, their blades precision machined from exotic alloys. Control rooms feature digital displays, automated systems, continuous monitoring. but the fundamental principle remains unchanged. Heat water to produce steam, use steam pressure to produce motion, extract work from that motion. The direct lineage from early engines to modern power plants is clear, even as the implementation has evolved beyond recognition. In contemplating steam engines, we confront questions about technology and progress. The steam engine was neither the first nor the last significant technology. It built on earlier innovations, metallurgy, mechanics, understanding of pressure and vacuum. It enabled later innovations, precision manufacturing, thermodynamics, electric power generation. Its impact was not predetermined. The same technology in different social contexts produced different outcomes. The specific path development took was contingent on choices by inventors, by investors, by governments, by workers, by consumers. The steam engine did not inherently demand factories or child labor or environmental degradation. These resulted from how the technology was deployed, from economic systems that prioritize profit, from lack of regulation protecting workers or environment. The technology enabled certain outcomes but did not require them. Alternative histories are imaginable where steam power developed differently, where its benefits were distributed more equitably, where its costs were borne less by the vulnerable. But history unfolds through specific circumstances, not hypothetical alternatives. What we inherit is the world steam helped create, with all its complexity, its achievements and its injustices, its opportunities and its constraints. Understanding this technology, how it worked, how it was used, who benefited and who suffered, informs how we approach contemporary technologies, how we might shape their development and deployment toward better outcomes. The smell of coal smoke, the hiss of steam, the rhythmic exhaust beat. These sensory experiences are mostly lost now, preserved only in the few places where steam engines still operate. Those who remember them from childhood, who grew up when steam locomotives still ran, when factories still used and saw steam power, describe a different sensory environment than the present. The smoke was not always unpleasant. On cold mornings, it carried warmth, a promise of industry, of activity. In towns where factories operated, it marked time. The morning whistle, blown by steam, calling workers to shift changes. The sound carried for miles. Locomotives approaching crossings, steamships departing harbors, factory engines starting or stopping. These sounds structured daily life, provided temporal and spatial landmarks, connected communities to industrial activity, even when they could not see it. The heat from steam systems was palpable. Engine rooms were warm even in winter, sometimes uncomfortably so. The radiant heat from boiler surfaces, from steam lines, from cylinders just after a power stroke, created microclimates, zones where workers sought warmth or fled from excessive heat, depending on season and task. These embodied experiences shaped relationships with technology differently than current experiences do. Steam demanded physical engagement, shoveling coal, oiling bearings, feeling temperatures with a hand to judge if they were normal. It was immediate, visceral, in ways that technologies mediated by screens and electronics are not. Whether this made steam better is questionable. The labor was hard, sometimes dangerous, often degrading, but it created forms of knowledge, of skill, of human-machine relationship that have largely disappeared, replaced by different forms that have their own character, their own challenges. The global spread of steam technology followed colonial and commercial expansion. Engines manufactured in industrial centers were shipped to colonies, to trading ports, to anywhere capital sought to establish production or transportation. Local workers were trained to operate them, though often without access to the deeper understanding that would allow innovation or significant modification. This created dependency. Replacement parts had to be imported. Expertise for major repairs resided in distant factories. The technology transfer was partial, sufficient for operation, but not for full mastery. Some regions developed indigenous steam manufacturing, creating engines suited to local conditions, local fuels, local needs. These industries sometimes achieved excellence, producing engines that competed with imported ones. But often, they operated in the shadow of dominant manufacturers, lacking the capital, the scale, the accumulated expertise of established producers. The patterns established in the steam era of industrial dominance, of technological dependency, of uneven development, persisted into later eras with other technologies. Understanding steam's global history illuminates these broader patterns, shows how technology and power, in both senses of the word, intertwine. Environmental consequences of steam power were significant, but went largely unrecognized or unaddressed during most of the steam era. Coal combustion produced smoke, soot, sulfur dioxide, particulates. Cities where steam power concentrated experienced air pollution that affected health, soiled buildings, reduced visibility. Rivers received thermal pollution from condenser cooling water, chemical pollution from boiler blowdown containing treatment chemicals, physical pollution from coal ash and slag disposal. The scale was small by later industrial standards, but locally significant. Landscapes were transformed by coal mining, mountains removed, valleys filled with spoil, streams polluted with acid drainage. The coal-fueling steam engines came from somewhere, and that somewhere bore costs not reflected in coal price, not borne by those who burned it. Forests were cleared for locomotive fuel in regions where coal was scarce. The massive consumption of wood by early railways contributed to deforestation, though this was later addressed by transition to coal or oil firing. These environmental costs were externalities, not included in the economic calculations that made steam power attractive. Had the full costs been internalized, development might have taken different paths. But the mechanisms for internalizing environmental costs did not exist. The understanding of long-term consequences was limited. The political will to regulate was weak. We see similar patterns today with contemporary technologies, suggesting that lessons from steam's environmental impact have been incompletely learned or imperfectly applied. The end of steam, when it came, was gradual. The last steam locomotives on major railways were retired over decades, gradually replaced by diesel-electric, The transition was not completed simultaneously everywhere. Some regions retained steam into recent decades, others abandoned it earlier. Industrial steam engines in factories mostly disappeared when those factories converted to electric drive, each machine with its own motor, eliminating the need for shafts and belts distributing power from a central engine. This transition offered advantages: flexibility in layout, easier control, better efficiency, but also represented the end of an era. Marine steam propulsion lasted longest in large ships, where steam turbines offered advantages, but eventually even these converted to diesel engines or gas turbines, more efficient, more compact, requiring smaller crews. The knowledge of how to design, build, operate, and maintain steam engines became niche expertise, preserved by enthusiasts, by preservation societies, by industries in regions where steam remained economical or where alternatives were unavailable. Educational institutions stopped teaching steam engineering except as history. Mechanical engineering curricula moved on to internal combustion, to turbines, to electric machines, to eventually robotics and mechatronics. The steam engine became a historical footnote, an example used to teach thermodynamic principles, no longer a living technology. Yet interest in steam persists. Preservation groups restore engines, maintain them in operating condition, demonstrate them to public audiences. Model builders create miniature working replicas, learning the principles by building at scale, where mistakes are cheaper, where materials are manageable. Steam rallies bring together enthusiasts, displaying engines, locomotives, traction engines, agricultural equipment. The machines are operated, their capabilities demonstrated, their history explained. Attendees include those who remember steam from their youth, those curious about the technology, children fascinated by size and motion and noise. There is something compelling about steam that transcends nostalgia. Perhaps it is the visibility of operation, the mechanical directness. Perhaps it is aesthetic, the shapes of cylinders and flywheels, the finish of polished brass and painted iron. Perhaps it is the sounds and smells, the sensory richness. Or perhaps it is recognition that these machines represent a particular moment in technological development, when human ambition to harness nature's power exceeded the existing capabilities, but human ingenuity rose to the challenge, creating machines that worked despite being built with limited materials, limited precision, limited understanding of the principles involved. The engineers who developed steam engines were not trained in modern thermodynamics. That science grew partly from analyzing steam engines. They worked empirically, building, testing, observing, modifying. They achieved remarkable results through practical knowledge, through persistence, through accumulation of small improvements. This empirical approach contrasts with contemporary engineering, which begins with theoretical analysis, with modeling and simulation, with understanding principles before building hardware. Both approaches have value, but the empirical approach fostered a particular relationship with machines, a knowledge grounded in physical interaction, in observation of actual behavior rather than predicted behavior. The steam engine serves as a reminder that technological change is not linear, that what seems inevitable in retrospect was often contingent in occurrence. Steam power, if developed differently, might have come earlier or later, might have taken forms quite unlike what actually emerged. The specific path taken depended on individuals, inventors who pursued particular ideas, investors who funded specific ventures, operators who preferred certain designs. It depended on circumstances, the availability of coal in certain regions, the needs of particular industries, the regulatory environments of different nations. It depended on accidents and luck, some promising approaches abandoned after early failures, some less promising ones succeeding due to fortunate circumstances. History does not reveal what might have been, only what was. But understanding that history was contingent, that alternatives existed, helps avoid technological determinism, the belief that current arrangements are inevitable or optimal. If steam could have developed differently, so too can contemporary technologies. The choices we make about development and deployment matter, shape outcomes in ways that are not predetermined. In the quiet hours before dawn, when most people sleep, the few remaining operating steam engines breathe. Fired overnight to maintain pressure, they idle, governors holding them at low speed, ready for the day's work, but not yet working. The fire glows in the firebox, coal burning slowly, just enough to maintain temperature. Steam pressure sits comfortably below the safety valve setting, bobbing slightly as the pressure relief valve breathes. Water in the sight glass holds steady at the proper level, the feed pump adding water as steam is generated. These hours are peaceful in the engine house. The equipment ticks and creaks as metal expands and contracts with temperature changes. Steam hisses quietly from packing glands. The exhaust from the idling engine puffs gently, unhurried, patient. The operator on night watch walks through, checking gauges, feeling bearings for temperature, listening for any irregularity. Everything is as it should be. The engine is content, waiting. As dawn approaches, activity will increase. The fire will be built up, steam pressure raised, the engine brought to speed to drive the day's load. But for now, in the quiet before dawn, the engine simply exists, a sleeping giant breathing steam. There is poetry in steam, in the transformation of water to vapor, in vapor's power to move massive machinery, in the cycle that returns vapor to water to begin again. The process is visible, comprehensible, grounded in physical reality. Water boils. We have all seen this. Boiled water for tea, watched bubbles rise, steam escape. Scaling this up to industrial proportions does not fundamentally change the phenomenon. It remains water becoming steam, observable, understandable. The pressure this creates pushes a piston. Not mysterious, not hidden in electronic circuits or chemical reactions. A piston, a cylinder, pressure on one side greater than the other, motion results. The directness is satisfying. The piston's motion turns a crank. The crank spins a wheel. The wheel drives machinery or propels a vehicle. Each step is mechanical, each connection visible, each transformation of energy traceable. This transparency made steam engines teaching machines, showing principles of thermodynamics, of mechanics, of materials science, of control systems. Students learned on steam not because it was the most efficient or modern technology, but because it revealed its workings, invited understanding. Modern technologies, more efficient, more compact, more capable, often hide their workings. The principles remain, but are obscured by complexity, by miniaturization, by processes too fast or too small to observe. Understanding requires abstraction, modeling, trust in theories that cannot be directly verified through observation. There is value in both approaches. Abstraction allows working with phenomena beyond direct experience. But something is lost when the connection between human understanding and machine operation becomes too attenuated, too dependent on intermediation. Steam, for all its limitations, maintained that connection. The operator understood their machine not just intellectually, but physically, through sensation, through experience, through years of interaction that built intuitive knowledge alongside formal understanding. The last segments of this history are being written now, as the few remaining enthusiasts maintain operating knowledge, as preservation societies struggle to fund maintenance, as museums decide what to keep and what to let go. Some engines will be preserved, maintained in operating condition, demonstrated to future generations. These will be the fortunate ones, kept alive through dedication and resources, teaching as long as they run. Others will be preserved but static, too complex or risky to operate, displayed as artifacts. They will teach through their presence, their scale, their construction, but not through operation. Still others will be lost, scrapped when the cost of preservation exceeds available resources, or allowed to deteriorate beyond repair, or destroyed by fire, or flooding, or simple neglect. Each loss diminishes the physical record, makes understanding the steam era more dependent on documentation and less on actual machines. The written and photographic record is extensive but incomplete. Operating procedures are sometimes documented, sometimes existed only as oral tradition. Modifications made by operators often went unrecorded. The subtle knowledge of how to coax best performance from a particular engine, how to compensate for its quirks, was rarely written down. Reconstructing this knowledge from documentation is possible, but limited. Reading about operating a steam engine is not the same as doing it, just as reading about riding a bicycle does not teach balance. Some knowledge can only be gained through practice, through mistakes and corrections, through physical engagement with the machine. This experiential knowledge faces extinction. As operators age and pass, as operating engines are retired, opportunities to gain direct experience diminish. Soon, those who operate steam engines will all be learning from preserved examples, from documentation, without the living tradition that previously passed from experienced operator to apprentice. This is the nature of technological change. skills associated with obsolete technologies disappear, usually without ceremony, noticed only by those who practice them. Blacksmithing, coopers, wheelwrights, countless crafts have faded as the products they made were replaced by industrial production or by entirely different technologies serving the same need. Steam operation joins this list, another skill whose time has passed, whose practitioners are few, whose future is preservation rather than practice. What lessons remain for those of us living in an era of different technologies? Perhaps humility about current technological arrangements, recognition that what seems permanent and essential now will someday seem quaint, will be replaced by alternatives we cannot yet imagine. Perhaps appreciation for the human ingenuity that solves problems with available materials and knowledge, that creates functional machines despite limitations that seem insurmountable. Perhaps awareness that technology's impacts extend beyond its immediate function, that introducing steam power reshapes society in ways its inventors did not foresee and likely would not have anticipated. Perhaps acknowledgement that technological change creates winners and losers, that progress for some means displacement for others, that managing these transitions with minimal harm requires conscious effort and is not guaranteed by market forces or technological capability alone. The steam engine does not answer contemporary questions. It is a technology of its time, suited to its context, eventually superseded. But studying it, understanding it, recognizing its strengths and limitations, its benefits and costs, offers perspective on our own technologies, our own choices, our own moment in the long arc of technological development. And so we arrive at the end of this exploration, having traced the development of steam power from early atmospheric engines to sophisticated triple expansion marine engines, from crude boilers to precisely engineered turbines, from individual machines to integrated systems powering factories, cities, transportation networks. We have considered the people who built these machines, who operated them, who maintained them, who were shaped by them, and who shaped the world through their use. We have acknowledged the costs in lives lost to accidents, in environments degraded, in social disruptions. We have recognized the achievements, the dramatic increase in productive capacity, the liberation from dependence on water and wind power, the foundation for subsequent technological developments. The steam engine stands in history neither as purely beneficial nor purely harmful, but as profoundly consequential, a technology that enabled changes whose ripples continue to affect us, whose legacy we inhabit whether we recognize it or not. In a museum somewhere, a preserved steam engine sits, its surfaces polished, its brass gleaming, its cylinder cold. It has not run in years, perhaps decades. It waits, patient as only a machine can be, for the occasional demonstration when volunteers gather, when funding permits, when interest warrants the effort of firing the boiler, bringing it to life one more time. When it runs, it speaks in a language of hisses and puffs, of rhythmic exhaust beats, of mechanical sounds that have grown rare. Those who hear it are transported momentarily to an era when such sounds were common, when steam powered the world, when these machines were not curiosities, but necessities. The demonstration ends. The fire is drawn. Steam pressure bleeds away. The engine falls silent, returns to stillness, waits for the next time, if there is one. And in that silence, we might reflect on our own technologies, our own dependencies, our own moment in the ongoing story of human tools and their consequences. And so, the narrative of this assembly comes to its quiet conclusion. Whether you are still awake, or whether you have already drifted into a deep and peaceful sleep, know that you are exactly where you need to be. The world is vast, but tonight, its systems are simply the backdrop to your rest. Thank you for joining me here at Quietly Made. Rest now. Join us again tomorrow. Good night.